we'll start that. Okay, so that's kind of funny. Where we left off is there we go. Had just done this problem, just guessing and checking, okay, guessing test, where we were trying to get the numbers in the triangle where each side added up to 12. Okay. And that was the last one we worked. And remember, in this section, we're just working our general problem-solving process, that Polya's problem-solving strategy had those 4 steps. Okay, so we just got a few more examples to do in this section, and then we'll start looking at chapter 2, actually, because this is the last section in chapter 1 that we're covering. So, okay, so this next one is kind of similar to this triangle thing. It's a little bit different. Okay, we're trying to make what they call a magic square. Okay. And the idea here, okay, we want all the rows, all the columns, and then the two major diagonals, so this diagonal and this diagonal, all to add up to the same number. Okay? And it gives us the numbers we can use. Okay? This one looks more intimidating than it really is because we've already got some of the numbers in the square. So we can't use them more than once, so we can mark off all the ones that are already in there. So 7's already in there, 12, 17, 22, and 27. Okay. So, come in. So it's not quite as bad, right? We don't have so many different possibilities we have to be concerned about here. One thing we do have to kind of pick up on, though, it says we want all the diagonals and all the rows and all the columns to equal the same number, or to be equal, but it doesn't tell us what number that is, so how can we figure out what we're trying to get our numbers to add up to? We've already got one diagonal filled completely out for us, right? So we can use that to figure out what the other ones have to be. So if we do 17 plus 22, that's 39. And 39 plus 27 is 66. 66. So that's our number we're trying to get on all the rows, all the columns, and all the diagonals. Okay. So then we can start plugging in the thing we want to think about where to start on this one is just we've got a few choices, but we want to pick somewhere where we've already got 2 numbers. That way we can figure out what the third number needs to be. So I don't know. Let's maybe this top box. You could start there or there or there. Yeah, those would be good. So maybe we'll start with this top box, and then really we've just got 4 numbers to pick from, so it's not too bad. Anybody see which one works? 66 is kind of big, so you might, if you need to use a calculator, that's not a problem. So let's see. Yeah, so, okay, I think I agree with that, because if we take 17 plus 7, that's 24. All right, so then 24 plus 42, that would be 66, and now we've used 42, so we can get rid of that one. Okay. And we can do any of the boxes now.
It's just that way.
Mm-hmm.
We can put 222.
All right, I think that looks like a good one. Yeah, so 42 plus 22 would be 64. So that's only 2 away. So yeah, we could put 2 down there. That's good.
37 at the bottom there.
All right. Thank you.
And then 32 and 27 and 27.
All right, so 37 down here, and then 32 is our other one. You're saying? And then we need to check. I don't need to check, so. This diagonal, we can't change it, so we're good with it. It's 66. this way, let's see, that's 59 plus 7, that's 66. This column is 29 plus 37, so that's 66. This one, 44 plus 2, 66. This one, 39 plus 27, that was good. Is that all of them? All the directions, I think we're good on that. Okay. So, those are not too bad. They look kind of scary when you, they don't look scary necessarily. They look like they're gonna take forever to try everything when you first look at all the numbers that's got listed out up there, but it's really not that bad. Okay. Any questions on that one? Anybody do Sudoku? Anybody play Sudoku? Have you seen that game a little bit? It's not the same, but it's kind of makes you think of it. Okay, it's not the same idea, but okay. Probably the same part of your brain you're using. Okay. All right. Let's see what's next. Okay. Let's take a look at this one. Yep. This one says find the sum of the numbers 1 through 1,000. So that's saying we want to do like 1 plus 2 plus 3 plus 4 plus 5 all the way up to 1,000. Okay. So need to come up with a strategy here. I guess you could technically brute force this thing. Okay. And you could get out the calculator and do 1 plus 2 plus 3 plus 4 plus 5 plus 6 all the way until you get to 1,000. But I don't want to do that. Okay? So let's see if we can come up with a better way here. This is a classic example you get in math class sometimes, because this is maybe legendary is better than classic here. There was a famous mathematician named Gauss, his last name, and back in the old days, like back hundreds of years ago, everybody didn't go to school and learn math, right? So if you had talent in some kind of field and you had money, then the thing that happened was that everybody had like individual tutors to teach them, right? So he had this math tutor that was teaching him math, but apparently that day Gauss was very annoying. He was really getting on his tutor's nerves. So this was like his punishment. His tutor was like, hey, go add up 1 through 1,000 and get back with me when you get that finished. It's like they go sit in the corner and work on this problem they gave him. And the legend goes, okay, that in like just a minute or two, he came back and had the answer. Okay, and that was way before calculators. Okay. So that story gets told to talk about how much of a math genius Gauss was. Okay? Saying that, we're going to figure out the trick here that he used, but saying that, I would not come up with this on my own either. Okay? So once you see it, it's not bad to do it again. Okay? But to just be some little kid sitting there figuring that out, that's supposed to tell how much of a genius he was. Okay? So doing 1 through 1,000, okay, that's a little bit of a challenge. So we can think about like a smaller version of this and see if we can figure out a way that would work. So that's our problem-solving strategy. We're going to solve a simpler problem. So maybe instead of 1 through 1,000, let's think about how we could do like 1 through 10. Okay. So here's the trick, and then see if you can figure out what's going on here. We're going to write them not necessarily in order, okay, the numbers. When you add numbers, it doesn't really matter what order you add them in. Right? 2 plus 3 is the same as 3 plus 2. So let's do it this way. Let's do 1 and 10, 2 and 9, 3 and 8, 4 and 7, 5 and 6. And I'm gonna add those up first. and then we can figure out our total from there, so. So if we do 1 plus 10, that's an easy one, that's 11. 2 plus 9, 11. 3 plus 8, 11. 4 plus 7 is 11. 5 plus 6 is 11. Okay. So that was their genius or creative or whatever you want to call it trick that guys came up with. So here, from here to get our total, every one of these is going to be 11. And then to get our total, we just have to know how many of them we have. We got 5. So if we want to know how much 5 11s is, we just do 5 times 11. And for doing 1 through 10, we would get 55, right? So we would just do 5 times 11, we get 55. Okay. So now we want to kind of try and take this trick and use it for 1 through 1,000. Okay. So I'm just gonna get this stuff out of the way here. Maybe. Okay. So the idea, we take the first number at 1 and then add the biggest number at 1,000. Okay. And then we would do the next, so 2 plus 999, and then 3 plus 998. So on these, when we add them up, we're going to get the same thing again, just like before, right? Because all we're doing is we're making the top number go up by 1 and the bottom number go down by 1. So when you add, you're going to get the same thing you got on the last one. Okay? But even this is a lot to write out, like trying to write. I don't want to list out all these additions either. So we can just kind of think about where we're going to end up, because we need to know how many of these things we're going to have. So what's going to be our last one? We're going up by 1 on the top, down by 1 on the bottom every time. And so they got to meet somewhere. 500, yeah. So we'll meet when we get to the middle, right? We'll meet when we get to the middle. So the top number will be 500, and then the bottom number will be 501. Okay. So if you list them all out, that's where we end up, right? That's like our last term there. Does that make sense? We got there a little bit? Okay. And then what are these adding up to? You're getting 1,001 on all of these. Okay.
Where did you get the 500?
The 500. Okay, so that's where, like our first one here, we start with 1, and then we're counting up on the top and counting down on the bottom. And the idea is that we'll end up meeting in the middle, right? Because we'll have 500 of these things. Because we're going to have, another way of thinking about it is we're going to have 2 numbers in each one of these. And then 1,000 divided by 2 gives us 500. That's another way of thinking about that. Okay. So, like if we had it all listed out, we would count up to 500 going this way, and then 501 to 1,000 going this way. Okay. So, how many of these do we have? How many of these 1,001s do we have? We got it up there. 500. Got 500 of them, and they're all 1,001. So to figure out our sum here, we do 500 times 1,001. Anybody put that in your calculator yet? What you got?
500,500.
Okay, yeah, that's it. 500,500. You probably wouldn't think it would be that big. I don't necessarily. You know, just intuitively looking at that, thinking about adding 1 through 1,000, but that was a big number there. Okay. So if you would not have come up with this idea on your own, don't feel bad. I would not have either. Okay. But now that we've seen the trick, okay, remember part of our problem solving process is reflection, right, and thinking about how it can help us later. So now that we've seen the trick, maybe if we have another problem that says add like 1 through 200, then hopefully this will come back to you, okay, and make that easier that way. Okay. So the idea on that one, their strategy, right, was that we, instead of trying to deal with the whole thing to start with, we just picked out a little baby problem, right? We picked out a simpler problem and figured out the trick there and then used it. Okay. Questions there? Okay. Well, all right, let's see what's next. Look at the next one here. Okay. All right, this one tells us our uncle is going to give us $1 on the day we're born, $2 on our first birthday, $4 on our second birthday. Keep doing that pattern where he's doubling the amount on each birthday. What we want to know is we want to know how much money we're going to get on our 18th birthday. Okay. So again, you could, if you really wanted to, you could like list them all out. Like I'm 1 year old, I get this much money. I'm 2, I get this. I'm 3, I get this. That's a little more work than I want to do personally. So if we can find the pattern, then we can do that without having to write so much down. So let's look at our pattern. So on our first, when we're 1, we get $1. When we're 2, we get $2. When we're 3, we get $4. No, sorry, I skipped over one, didn't I? When we're 1, we're born. Sorry, that's what I messed up. Thanks. When we're born, we'll call that year 0. Okay. We'll get $1. 1, we get $2. 2, we get $4. 3, what would it be? Not because we're 8. It'd be 8, right? Because we're doubling, right? So we're doubling the amount we got on the last birthday every time. Right? So we want to figure out on our 18th birthday, how much do we get? Okay. So you may see a pattern. This one can be a little tricky, but the fact that it's doubling, what's another way of saying we double something? What's like the mathy way of saying that? If we double something that's like, okay, no, but hold that idea. We're not squaring, we're multiplying it by 2, multiplying it by 2, okay? And multiplying it by 2. So each birthday we're multiplying by 2. So square means you multiply it by itself, right? But that's a good thing to have in your mind though, right now, squaring. So anybody see a pattern? A little tricky to see. All right, let me give you a head start. So what if, instead of writing the first one on our birthday or when we're born as a 1, what if we wrote it as 2 to the 0th power? Anything to the 0th power other than 0 is 1. Okay. So then 2, we could write that as 2 to the 1st power. What about 4? How can we rewrite that? It'd be 2 to the back, I guess, on 8. Yeah. You seeing the pattern? So when we're 0 years old, it's 2 to 0. When we're 1 year old, it's 2 to 1. 2 years old, it's 2 to 2. 3 years old, 2 to 3. So what's it going to be on our 18th birthday? 2 to the 18. 2 to the 18. So if we can pick up on that pattern, it's a little tricky to see. If we can pick up on that pattern, then we can figure out that on our 18th birthday, we'll get 2 to the 18th dollars. You got it?
It's 4,096.
Uh-oh, nah.
I
Think you gotta go again.
I think I might have done it too much.
Yeah, so one way, yeah. So another way you can work this problem, okay? And it's, all we're doing is we're doing the same thing, but you're not necessarily thinking about it as an exponent. But one way you could work this is we could say, okay, I'm gonna start with $1, and then I know I double it, and then I double it, and then I double it. So 2 times 2 times 2 times 2. So you could in your calculator, you know, do like 1 times 2 times 2 times 2 times 2 times 2 and count it 18 times.
Yeah.
You have to be careful though, because you can go one too many or one too few really easily. So another way you can do it is do it with the exponent. Right? So you can do 2 to the 18th power, and then somebody had it. What'd you get? 2. Yeah, that's it. So on our 18th birthday, we get $262,144. Wow. That's the kind of uncle I want. Yeah. That's a pretty good birthday. Are you unimpressed with that? Would you wouldn't be impressed if you got $250,000 for your 18th birthday? No. That's it. That's it on that one. Okay. But if you didn't see the 2 to the something power, you could do it the other way, right? We know we're doubling, so you just do 2 times 2 times 2 times 2 times 2. That's the same thing. Okay. You get the same place. Just a little more error prone. You have to be really careful on counting. Let's look at the next one here. We just got 3 more in this section. So this one and then 2 more. Okay. All right, so we've got a baseball league. It says each of the teams are going to play 4 games against each of the other teams. And we got 5 teams in the league: Raiders, Jackals, Blazers, Warriors, and Eagles. And we want to know how many total games are going to get played in the league. So you could try to just kind of keep up with it. Like you could try to figure out how many games each team was going to play and work it out that way. It's really easy to make a mistake doing that. So our suggestion here is to draw a diagram or make a little sketch. And I think that works really well on this one, so we can do that. And so what I'm gonna do, they were nice to us, okay? They gave us 5 teams that all started with a different letter. So we can just use the first letter and not have to write that whole thing down. So what do we have here? Raiders, Jackals, Warriors, Blazers, and what was the other one? Eagles. A little bit of trivia in case you're ever on Jeopardy or something like that. Or you need to win a bet or something like that. You know the most common mascot in the United States? I got a guess? No, that's my high school's Bulldogs, but no. Eagles. Eagles is it. Okay? Eagles is the most common mascot in the United States. So. Okay, how many of you went to a high school that was Eagles? Nobody? Wow. Boy, that was struck out on that one, didn't I? I was expecting like 2/3 of you to go as Eagles. Man, I didn't go that great. All right. So, one thing on making this diagram, it tells us that each team's going to play 4 games against all the other teams. So my idea here is just to draw lines between the teams when they play. But if they're all playing 4 games against each of the other teams, that's going to get really messy. Since they're all doing that, we can clean it up a little bit if we just draw one arrow and just remember that that represents 4 games. Okay? So that makes our picture not quite as hard to decipher. Okay? So I'm just going to start matching up the pairs, and you can start anywhere you want to on these. I guess I'll start at the top. I'll start up there with Raiders. So then we know the Raiders have got to play the Jackals. They got to play the Warriors. Got to play the Blazers. They got to play the Eagles. Okay. We just have to remember each line's 4 games. Okay. So you can go anywhere you want to next, but I'm just gonna go clockwise, I guess. So I'll go to Jackals, and since I can up here, I'll switch colors. Okay, so the Jackals, we don't have to fill in as much because we've already got their 4 games with the Raiders. Okay? That's where you come into potential problems if you just try to list it out and try to figure out how many games each team's playing. It's really easy to accidentally count one twice. Okay? So we don't have to do the J and the R again. We just need to do JW, JB, JE. Okay. And we can do the Warriors, and I'll switch again here. So Warriors, we've already got the Raiders and the Jackals counted, so we just need to draw in the line for the Eagles and the Blazers. Okay. And then for the Blazers, we've got 3 of their games already, so we just need one with the Eagles. Okay. So then, now we can count our lines. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines. Okay, but what did we have to remember? That's not 10 games, right? We've got 10 lines, but each line was 4 games, right? Yeah, so we just got to multiply by 4. So 40 total games. And again, you could probably come up with another way to work that one, but and that would be okay. That's what we did on that one. Okay. Well, look at the next one here. Okay. So it says, how many ways can you make change for 50 cents out of quarters, dimes, or nickels? So we're thinking about like combinations of quarters and dimes and nickels. Okay. So on this one, if you kind of try to take the brute force route and just think about the different ways you could do it, it's easy to, there's more than you would probably expect, more different ways you could do it, and it's easy to miss one, something like that. So that's why they give us a recommendation on our strategy of making a list. Okay. Way we can be kind of organized, be kind of systematic about it. So we can do that, and so all I'm going to do is I'm just going to make a little table, and I'm going to write Q, D, and N, and then we'll just keep track of how many each those each of those we would use. So, and the way I'm gonna do it, because I'm trying to be careful and not miss any, I'm gonna start with like the most quarters I could use, right? And then work my way down. So I'm gonna try and do it in the fewest number of coins first. You can think about it that way too. And then work my way down. The most we're gonna have is if it's all nickels, right? So work my way down to that. So, okay, easiest one, if you're gonna end up with 50 cents, we can do that with 2 quarters. Do that with 2 quarters. No dimes and no nickels. And that's the only way we can do it with 2 quarters. Right? So instead of using 2 quarters, we could use 1 quarter. Okay. And then if we tried to get the most dimes we could from there, we could do 2 dimes in a nickel, right? Because if you have 1 dime in a nickel, that's 15. Right? So you had to go 2 dimes in 1 nickel. Yeah. Or we could do 1 quarter and then 1 dime. And how many nickels do we have then? 3. Yeah, that's it, 3. So we can kind of find a pattern here too, and it'll help us. So every time we get rid of a dime, we have to add 2 nickels to make up for that dime, right? So we went down 1 here, so we've got to go up 2 nickels there. So that helps, okay. Or what could we do? We could do 1 quarter and no dimes. And how many nickels? 5, yeah, 5. Okay. All right, and then I'm out of room, so I'm just gonna duplicate my table here and keep going. Okay. So, and then there's no other way we could do it with 1 quarter, so next we'll start using no quarters. So what's the most number of dimes we could use then? 5, yeah, we could do 5 dimes and no nickels, so it would be 50 cents. Okay, or 4 dimes and 2 nickels, or 3 dimes and 4 nickels, or 2 dimes and 6 nickels, or 1 dime and 8 nickels, or what's the last one?
10 nickels.
Yep, 10 nickels. Okay. So how many have we got there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 different ways, right? I don't know, to my brain, when I just first look at that question, it doesn't seem like you should be able to do it that many different ways, but. Get there, so. Just making a list, and again, we're just trying to be organized, so you want to kind of try to have some kind of method that you're using. It doesn't have to be starting with the most quarters and ending with the most nickels, but you want to try to have some kind of method so you don't accidentally miss one. Or accidentally do one twice. Those would be the 2 common mistakes there. Questions on that one? Not too bad. Okay. One last one. Okay, we got one last strategy we're going to use, and this one is a little bit like algebra. Okay, we're gonna avoid algebra type stuff in here as much as we can. But it is really useful, so at least the basic stuff out of algebra is really useful. So we've got this mathy statement here. It says, taking a number and multiplying it by 8, the product is added to 6. If the sum is 30, what was that number? Okay. So our suggestion here is use a variable. And that does work really well on this one. So where we need a variable, we just need to have something to represent this mystery number we're starting with. You can pick whatever variable you want to. You may have a suggestion. Yeah.
3.
Please answer. Well, I'm talking about suggestion for the variable. What you got? X, okay, well that's fine. That's the classic go-to. But you don't have to use X. If X gives you anxiety,
All of it give me
if X gives you anxiety, you use something else. Okay, so pick whatever you want to. You can use N for number, or if you could use a question mark if you really wanted to. It's just unknown. So okay, so we've got our mystery number now. Now we just need to keep up with what's happening to it. So first it says it's multiplied by 8. Okay, times 8. And then that product is added to 6. So plus 6. And then it says if that sum is 30, so it's saying if we add those two things up, we get 30. Then what was our number we started with? And that might look weird if you want to write it 8x like you normally would in algebra class, that's fine. You can switch the order there. And it's just basic equation solving, nothing too complicated. You remember if we're trying to figure out what x is, what our first step should be there? Oh, you're being quiet today. Got it. The first step. Yeah, it's track 6. Track 6, okay. These cancel, and then 24. And then the next step, divide by 8 on both sides. Good. Yeah. And then we get x equals 3, so. Remember, if we're trying to grow through this problem solving process, the thing we should do, we should make sure our answer makes sense, and if we can, we should check it. So let's walk back through it. Instead of saying a number, we can say 3 is multiplied by 8, so that would be 24, and that product's added to 6, so that gives us 30, so that works out. It works out. Okay. So we'll try and stay away from algebra type stuff as much as we can in here, but sometimes it's just really the best way to solve a problem. Okay. Questions on that one? All right, that's it for chapter 1. Okay. So chapter 1 is behind us now. Okay. So anybody remember when 1.2 is due on Hawks? Yeah, I can't remember either. Let me look now. Yeah, when it was due. I was just going to give you a reminder. It's not till like next week sometime, but is it still Monday? Let me look. Let's do. Okay, actually, I have it due September 1st, so that'll be on Wednesday night. Okay, so the first one, 1-1's due Monday. Okay, and then the next one's due 25th. Okay, is due the 1st. Okay. So just wanted to be able to give you a reminder there. Okay. All right. So at least part of another section today. Cool. Get out of here in just a little while. Okay, not yet. We'll get. So the secret on taking a class, especially when you get toward the end of the week, is that the teacher wants to go home too. Okay, the teacher wants to get out of here too. So, but we've got stuff we need to get through. So, okay. All right. So moving into the new chapter, the rest of the chapters, okay, we kind of had the general problem-solving chapter. The rest of the chapters, we kind of visit a different area of math, a different branch of mathematics as we go to each new chapter. So in chapter 2, the area of math we're looking at would be called set theory. Okay? So 2.1, we're going to look at the notation we use with these things called sets. So set theory is like if you went and got the PhD in math, you could spend like, you could specialize in set theory. But we use sets in pretty much all the other branches of math too. Okay, so it's a really widely used idea. Okay. And you might not realize it, but you use sets too. You just might not call them sets. So we want to really, for today, the main goal, it says develop an understanding of set operations, but really the first thing we want to do is just get the vocabulary under our belt, okay, and get the notation down. Okay. So, anybody ever organized their closet before? Yeah. If you've done that, you've used sets. Okay, if you've organized anything, you've used sets. Anytime you group something together, you say, oh, these things are all similar to each other. I'm going to group these together for whatever reason, and you use sets. So you might not think about it in the mathematical set way, but you're using the idea, okay? Even if not. So anytime we have a system to group things together, we're dealing with sets, okay? This is one of the areas where the math that we're dealing with doesn't necessarily have to do with numbers. Okay? You can use sets to work with all kinds of things. Okay, it doesn't have to be numbers. So big idea there. Okay, so let's get our definition. Definition for a set here is very general. Okay. Not a lot. We're not specifying a whole lot here. It just, when we talk about a set, okay, we just mean a collection of some object. Okay. And it could be a set of kitty cats. It could be a set of irrational numbers. Okay. It doesn't matter. Okay. It doesn't have to be what you think about a math object. And then we actually have a little bit of vocabulary within the vocabulary here. These objects that are in a set, we call those elements or members of the set. Okay. And that's it. And that's all the definition. It's very general, so you can use it for a lot of different things. Okay. All right. So the next thing we need to talk about is how we write down a set, okay, how we specify a set that we want to use. Okay. There's actually a couple of ways we're going to look at doing that. The first way we're going to look at how we can write down a set is called the roster method. Okay. So what's a roster? What is that? Yeah, it's really just a list. Yeah, it's just a list. So, like our attendance sheet, this is like our class roster. I just list out the people in here. Or if you have a sports team, you say you see the list of the roster. That's just the people on the team. Yeah, so that's all roster notation is we're just listing out all the things that are in our set. Okay. All right. And the way we do that, we kind of have you can think about it like grammar, sort of, for math class. That's what we would call notation. Okay, we have a standard way of doing that. And the way we write down a set is in roster notation. Okay? So just in general, no matter what method we use to write a set down, the common practice, it's not always, but usually when we're given a set a name, we use a capital letter, an uppercase letter. Okay. And then we'll have an equal sign. And then we have these curly brackets, what do I call those? Okay, these curly bracket on each end. And then here in the roster method, we just list out the stuff that's in our set. So, and we put a comma between each thing. So we would say set A is the set that has members 1, 2, X, Y, and Z. Okay. So they're just listed out there. Okay. So that's roster notation, or the roster method. We just list out the things that are in there. Okay. So when we have a set, or maybe we have two sets actually, okay, we just list out the elements that are in there. And if you're thinking about like math stuff that we do, right, like if we have numbers, one thing we like to talk about with numbers is whether or not they're equal. Right? Do they have the same value? Okay, so talking about whether or not two sets have the same value is tricky, to think about. Okay, but we do have a definition for what it means if two sets are equal. Okay, so that's our next slide here. Okay. So we say two sets are equal if they contain exactly the same elements. Okay. So we'll have set A over here, and we'll say it contains the letters A, B, C. Okay. And then if we had set B over here, in order for them to be equal, they have to contain exactly the same elements. So one thing though that you should pay attention to is that they don't have to be listed in the same order. And just as long as all the same stuff's in there, it doesn't matter what order you write it down in. Okay. And then our notation we use for that is just a normal equal sign, so nothing new there. Okay, but in this case, we could say these two sets, set A and set B, we could say set A equals set B. Okay. Because they have the same members. Okay. Questions there on that definition? No, it's not too complicated. Okay. That's what we mean if we had two equal sets. Okay. All right. So next, okay, something else that's nice to be able to discuss when we're talking about sets is how many members they have in there. Okay. So we have a name for that. Okay. The name for that is set's cardinal number, the cardinality. Okay. So all we're doing with the cardinality or cardinal number is we're just talking about how many things are in each set. Okay. So like here we would say how many elements are in here. It says 3, so the cardinal number is 3. Okay. And our notation we use, it looks weird up here on the slide because it doesn't have anything in there, but it's just like the absolute value symbol. Okay. It's the same thing as the absolute value symbol. If you remember it, it's just the two vertical bars. So like here we could say the cardinal number of set A is 3, and that just means we have 3 members in there. Okay. 3 elements. Okay. And then here we've got 3 elements again, so cardinal number of set B would also be 3. Right. Then I've got an extra little question down there. Does set A equal set B? No, it doesn't. Why not? Remember our definition of being equal? They're not equal because what do we have to have? We have to have exactly the same elements to be equal, but on this one, they're not exactly the same. This one's got ABC, this one's got BGH. Okay? So these are not equal, but their cardinal numbers are the same. They have the same cardinality, you can say that. Okay. Questions on cardinal number? Okay. So this relationship though, where two sets have the same cardinal number, that's still something that's important to us because that's something good to know. Okay? You can say two sets are the same size even if they're not equal. Okay? So we have a weird thing with sets that you don't have with just numbers. So instead of being equal, if two sets have the same cardinality, we give that another name. Okay? Oh, sorry, we'll come back to that. Forgot that was there. Give that another name. That said, the two sets are equivalent. That's what we call it if they have the same cardinality. Okay. Same cardinal number. Okay. And to write that, our notation, our little symbol we use is the squiggle, okay, is usually what I call that. But just if you want to know, the official name for that little squiggle symbol is the tilde or tilde. I've heard people say it both ways. Okay, and it's on the keyboard. You don't use it much, but the little squiggle's on there. Okay. So if we have that squiggle, that means they have the same size, the same number of elements, but
Like so, one has three. If one has three numbers.
Yep. So here, right, on these two, right, these two sets are not equal because they don't have the same elements, but they have the same cardinal number, so they are equivalent. So you could say A squiggle B, and that would be true. Yeah, that's right. Okay. Yep. Okay. All right, so let's look at an example here of roster method. I forgot first to do that. Okay. And I forgot to, I forgot to erase my slides first to have to do geography, so you get out of doing geography today. But this one says, use the roster method to represent S, the set of states in the United States that begin with the letter M, and then find the cardinal number of S. So we've got all of our states there. I can never remember how to spell Massachusetts, so I abbreviated. Okay. And then how do we come up with this? How do we come up with the cardinal number? Yeah, we just count how many are in our set, right? We just count how many are in our set. So as long as you don't miss any, you get them all in there. And we've got 8 states that start with the letter M, so our cardinal number there is 8. Okay. Anybody know how to spell Massachusetts?
M-A-S-S. I'm from there. M-A-S-S-A-C-H-U-S-E-T-T.
All right, well, that's good. Hard to say it out loud instead of writing it, isn't it? Yeah. That one trips me up a lot, so. Okay. All right, let's look at this one last example, okay? Now, we're running early in here, that's okay. I mean, who complains about that? Let's look at this one last example here. So here we just got more sets and we're thinking about equivalence and equal. Okay. So on A here, we've got, it looks like college majors listed. Okay, and then B, we've got these names. So if we're asked if these are equal, they're not equal, why? This set and this set, they're not equal to each other, why? They don't have any of the same stuff in them, right? This one has college majors, this one has names, so they're not equal. But if we count carefully, because this one's split between two lines, okay? If you count carefully, set A has 1, 2, 3, 4, 5 elements in it, 5 members. And then B also has 5 members. So they have the same cardinal number, so they're not equal, but they're equivalent. Okay? Because the cardinal number of A is the same as the cardinal number of B. Okay, so the other thing we could write there is that A is equivalent to B. And then on example B, okay, we've got set X and set Y. So are those equal? I'll get my head on. Are they equal? They are, but what do you notice about the two sets? Yeah, they're just reverse order. Okay, they're just reverse order, but they have the same. If you check it, they have the same numbers in there, the same members. The order's different, but the same stuff's in both of them, so they are equal. Okay. And if you count them, you really don't have to count them, but if you do count them, they have the same cardinal number. So not only are they equal, they're also equivalent. Okay. So A, they're not equal, but they are equivalent, so that can happen. But in the second situation, why I said you really don't have to count them, is if they're equal, that means they have the exact same members. So that automatically tells you what about how many they each have. Has to be the same, right? You have to have the same number of elements in both of them in order for them to be equal. So if you know two sets are equal, you automatically know that they're equivalent. Because they have to have the same number in both for them to be equal, so that's what being equivalent means. They have the same number in both. Okay. Questions here? We don't have much left in this section, but it's fine. We'll pick it up next time. We'll have to push a little bit harder next week because we're missing the Monday after that. Okay, not next Monday, but the Monday after that's Labor Day. So we'll only meet one time that week. So,
When will you
Post which part? I'm sorry. Oh, the notes. As soon as this is over with. I should have done it before class, but I forgot. So, yeah. Oh, if you came in and or if you got missed and you get on the sign-in sheet, I'll put it up here on the front table so you can get on it on your way out. Okay?
Yeah.